So let's consider the basic parameterization of a circle. So we'll use a unit circle. And back in the beginning of the trig, we defined this function called the cosine based on the angle from the positive x-axis to the radius, and that x value is the cosine of theta, the angle. Y value is the sine of that theta. We can tweak this a little bit by saying, what if we try x equals twice the cosine of theta and y equals twice the sine of theta? And what we're going to get then is a circle of radius 2 coming around here. Oops, a little messy. When we do that. Now, what if we don't use the same number for each of these? So for example, what if we try x equals 3 times the cosine of theta and y equals twice the sine of theta? What's going to happen? Well, at the angle 0, cosine is 1, so for sure I'm going to get that point right there. And the sine, when theta is pi over 2, is going to be 1, so for sure I'm going to get this point up here, and so coming around, I'm going to get those 4 points. And that's the cosine value is always going to be 3 times longer than it was on the unit circle, which is just going to put all those x values out this way more. And the y values are only going to be 2 times longer. So what we're going to get is we're going to get a circle that is stretched in the x direction, but not the y. So we're going to get something that looks like this. And this shape right here is called an ellipse. Now, relationship between x and y and theta and our radius here is that x squared plus y squared is equal to the radius squared. And if we put that together and we just focus on the unit circle parameterization, then we get a 1 squared over there. And we are just substituting in x is 3 cosine theta and y is 2 sine theta. Now here I got to do a little bit of work because on the unit circle, x has to be the cosine. So I have to actually solve this one for the cosine. So if I solve that one, I'm going to get the cosine of theta is equal to x over 3. And here I have the sine of theta is going to be equal to y over 2. And if this were the unit circle here, we would also write it as cosine of theta squared plus sine of theta squared is equal to 1, right? Our Pythagorean identity. But now, based on this new parameterization of this thing, I'm calling an ellipse here, I know the cosine is really x over 3. So that's going to give me the square of x over 3 and the square of y over 3, or 2, sorry. And that has to be 1. And then squaring this multiplies it by itself, so I could write that as x squared over 3 squared plus y squared over 4 squared, or 2 squared, which is 4. So we can parameterize an ellipse based on the idea of a circle centered at the origin. And if we change that parameterization into a Cartesian equation, we can use the Pythagorean identity to do that, and we get an equation that looks like this for an ellipse. Now in Cartesian, I can shift things easily left and right and up and down by just altering this a little bit. And so the general form for an ellipse is x minus h squared plus y minus k squared. And then we have divided by our a squared here. And that's like my 3. A is 3 here. And then here we have the y minus k squared over b squared. So here my b is 2. And hk is the center. Because I am shifting it by h horizontally, and I'm shifting it by k vertically here. So this is the general form for ellipse in Cartesian. For an ellipse in parametric equations, it would look like x is equal to a cosine theta plus h, and y is equal to b sine theta plus k. Would be a parametric version of an ellipse centered somewhere else besides the origin, right? We just shifted over h, shifted up or down k. Oops, no, I want that back. Next page. Now, there is another way to view an ellipse besides a distorted circle. Definition of ellipse is the set of all points for which the sum of the distances from two focus points is constant. So let's take a look at that here. So here I graphed an ellipse and I set A to be equal to 4. And I set B, let's see, A equals 4, there we go. And I set B equal to the square root of 7. That's supposed to be a B, not an H. And my claim is that if A is 4 and B is 7, then my focus point, and I center this at the origin, that my focus points here will be at x equals 3 and x equals -3. And so then any point I pick here, so I'm just going to pick some other point here, x, y, the set of all points for which the sum of the distances to the focus points is constant. So here's a point on the ellipse, right? That's my set of all points, the ellipse. And I say these are my focus points, the -3 and 3. This point xy here, which could be any point on the ellipse, I want to find the distance to one focus point and the distance to the other focus point, and I want to add them up. And the catch is it doesn't matter which point I pick, they're always going to be that same constant here. So whether I pick this point xy, or I pick this point on the y-axis, or I put this point on the x-axis, the sum of the distances from any point on the ellipse to those two focus points is always going to be that same number. So one thing you could think about is if you put 2 pins on a piece of cardboard and you take a string that is longer than the distance between those pins, and you attach the string to those pins, and then you put your pencil tight in the middle of that string, and you just hold that tight and trace that around, you'll get an ellipse. If those two focus points happen to be the same point in the middle, you'll get a circle. So the closer these two focus points are to each other, it looks more and more circular. If these 2 points sit on top of each other, then you get exactly a circle. All right, so let's just play around with this idea a little bit. So again, the sum of these two blue lines should be some constant value, and it doesn't matter which point I pick, so I'm just going to pick a different point. I'm going to focus on this point up here at the top for a second. And so then the distance from that point to the focus plus the distance from this point to the focus, that's those two red lengths added up are the same as those two blue lengths added up. Okay. Now, what if instead I picked on, use a highlighter for this one, I picked on, say, this point over here. What am I going to get? Right, so I'm at that point right there. Well, the distance from this point to either focus, that's going to be this distance right here plus this distance right there. And if you think about those two distances together, this first distance I mentioned, let's use green here, this one right here, that's the same as that distance right there. So if I'm talking about this point on the x value, we call that a vertex of the ellipse on the major axis, because the major axis is the longer axis. The combination of those two distances to the foci is the same as the distance all the way across the major axis here, right? Because I have this chunk here, which is the same as that chunk here, and then I have this other chunk here. So I've covered that whole distance exactly once. So by looking at this ellipse, I can tell you what the combination of those two distances is, that constant value. So that constant value I'm going to call it C, is equal to 2 times the distance from here to here, right? That's my 4, and that's my value I'm calling A here. Okay, so that constant C, the length of that string, which connects any point to the 2 foci, is always going to be twice the distance from the center of the ellipse to the vertex on the major axis there, or it's the distance across the major axis here. 2a is that distance across the major axis. So if we know some information about the major axis, then we know the foci. And it turns out it goes further than that. If we focus on, let's use the red highlighter here. If we focus, is that the highlighter? No, highlighter, red, okay. If we go from this point, this vertex on the minor axis, the shorter axis, then the diagonal connecting that minor axis vertex to the focus and then back to the center, that forms a right triangle. And this diagonal length here, right, that length right there is the same as this length down here. And so there's a relationship here between A, B, and C at the focus. So I just want to redraw that on the side here so we can see it. So here is my center. And then on my ellipse, I drew that out 1, 2, 3, 4. And then I had my focus right here. And then square root of 7 is about 2.6. So 1, 2.6, that would be up here. About, so there's my square root of 7. There's my 4 there. And I've got my 3 here. And then my ellipse, let's just draw a quarter of it here. It's going to look something like that, a quarter of it. And then if I draw a triangle from the center using the minor axis point, let's choose red. So if I draw this triangle right here, that diagonal, because of this relationship here, is going to be the same as the length, half the length of the semi-major axis. So what I have in terms of my A, B, and C, that constant there, I get this is B right here, this is C right here, and that is A right there. So it's not quite the Pythagorean theorem, right? It's written a little bit different, even though this is a right triangle. And so then I get that let's focus on the foci, C squared is going to be equal to A squared minus B squared for an ellipse. And these two numbers right here, right, those are the distances from the center to the vertices. And then C here, right, that's the distance from the center to the focus. And those help us piece together information about an ellipse, whether I need to know the vertex points, right, those extreme points along the major and minor axes, or whether I need to know the focus points. Now, you might say, well, why the heck do I need to know the focus points? Because they're not even on the graph. So what about this definition, right? I have this equation right here. Good point. So why? Who gives a shit? Show you. So let me draw again my best ellipse, something like this right here. There's my best ellipse today. And this ellipse has a major axis. Major axis is always through the longest part of the ellipse, and the minor axis is always through the shortest part of the ellipse from a central point inside the ellipse here. And then the focus points always live somewhere on the major axis, and they're equally spaced from the center here. Cool thing about an ellipse is, let's suppose that this is like a pool table here, and I have a ball sitting right there. If I shoot this ball at the edge, let's see, am I lying about this? No, I don't think so. Maybe I am. Let's see, pool table is not the way to think about it. Let's think about it in terms of sound waves. There we go. If we broadcast sound out from this point right here, it's going to bounce all over the room. But because of that relationship between these 2 points and points on the ellipse, there's this special connection to these 2 points right here. So the strongest signal from this point here will be received at that point right here. So if you make a tiny sound right here, then what's going to happen is, although sound's going to be broadcast all over the place, the strongest signal will appear right here. So if I'm standing over here, I'm really not going to hear that very well because the sound waves really aren't bouncing in my direction. But if I stand here, I could hear a whisper that I couldn't hear here or here or here very well because of that connection there between the ellipse. If you've ever been in a dentist's office, they have these mirrors up above that have these curve to them, and then your mouth, right, is down here, and they're saying, say, ah, and you're like, ah, and they have this little light right here, and that light is an elliptical curved mirror, so that the strongest signal from that light is going to end up at the other focus, which is going to be in your mouth there, which is kind of cool. So that's why we care about the focus of an ellipse.